So far, all of the differential equations that we've seen have generated pristine deterministic solutions. Sure, some of the solutions may have been chaotic, but we could always calculate the values at any time t, given the initial conditions. And because the solutions were deterministic, if you use the same initial conditions that I used, then your solutions should have been the same as my solutions. But the real world is not as predictable, so it's a challenge to align our solutions to observations in the field. One of the ways to make differential equations more realistic is to add some noise to our equations. The term stochastic just means determined randomly, as opposed to deterministic, which means determined without any randomness. How can we use the DifferentialEquations.jl package to solve stochastic differential equations in Julia? Well, let's find out. Welcome to Doco.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. I'm assuming that you've watched the first 11 episodes of this series, so I'm assuming that you know how to use Pluto notebooks and that you know the basics of the Julia programming language. I'm also assuming that you know how to use the DifferentialEquations.jl package in order to solve first-order ordinary differential equations, second-order ordinary differential equations, and systems of differential equations. With that said, let's get started. Let's start by firing up the Julia REPL and launching Pluto. Next, let's create a new notebook and title it Stochastic Differential Equation. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. Just for reference, I'm going to add a couple of links. The first link is for the Wikipedia article on stochastic differential equation. The second link is for the DifferentialEquations.jl package documentation. Next, let's add a few packages. Now that everything's loaded, let's describe the problem that we're trying to solve. A stochastic differential equation is just a differential equation plus some noise. I took this LaTeX from the DifferentialEquations.jl package documentation. The first part of this equation you've seen before. That's just the equation for an ordinary differential equation that defines how some unknown function u changes with respect to time, and is impacted by some parameter alpha. The second part is new. That's the stochastic part of the equation. The second part of this equation defines how that unknown function u changes with respect to this uppercase W, which stands for the Wiener process. The Wiener process is named after the American mathematician Norbert Wiener. This process is the one-dimensional Brownian motion. Brownian motion is named after the Scottish botanist Robert Brown, who in 1827 first described the multidimensional random motion of particles suspended in a liquid or a gas. So to recap, Brownian motion is random motion in multiple dimensions, and the Wiener process is random motion in just one of those dimensions. In other words, the Wiener process defines some random noise, which is also referred to as white noise. Now that we know what we're working with, let's set up two Julia functions. One for the standard ODE without any randomness, and the other for the white noise. Okay, now that we've defined the Julia functions, let's assign the variables. As a motivating example, I'm going to use a modified version of the continuous compound interest problem that I covered in episode 704. As a reminder, the continuous compound interest problem revealed that if you start with an initial quantity of 1, subject to a continuous compound growth rate of 1, and applied for a time period of 1, then the ending quantity at time 1 will be 2.718, which is Euler's number. For the beginning quantity, let's set the initial value at 1. The parameter alpha is the continuous compound growth rate. Let's bind alpha to a slider with a default value of 1. The parameter beta is new. This parameter controls the magnitude of the noise. A low value means just a little noise, and a high value means a lot of noise. Let's bind beta to a slider as well, but let's set the default value to 0, which means no noise at all. For time, let's just fix the time span between 0 and 1. In order to solve the stochastic differential equation, we're going to use a solver called EM. I'll discuss the solver in a little more detail in a few minutes, but for now, all you need to know is that this solver requires a time step, which I'm setting at 0.0001. Okay, now that we've assigned the variables, we can define the problems. We need to define two problems. The first one is for the ODE without any randomness, which we'll use as the control. And the second problem is the SDE, which is just the ODE plus some noise. Okay, now that we've defined the problems, we are now ready to solve them. Because we have two problem definitions, we need to use the solve function twice. This solution should look familiar to you, since it's the same solution from episode 704. Notice that the ending quantity is 2.718, which is Euler's number. Before we solve the SDE, let's set up a Pluto UI button that we can use to generate a new solution whenever we click on the button. In order to solve the SDE, we need to use an SDE solver. The solver that we're using is named EM, which stands for the Euler-Maruyama method. The method is named after the Swiss mathematician Leonhard Euler and the Japanese mathematician Yujiro Maruyama. Maruyama is noted for his contributions to the study of stochastic processes, and the EM solver is a method for the numerical solution to stochastic differential equations. The EM solver requires a time step as a keyword argument. As you can see, the SDE solution looks very different than the ODE solution. but it's difficult to tell if anything's going on just by looking at these numbers. So let's plot the solutions to see what they look like. Let's start by plotting the ODE solution. This plot should look familiar to you, since it's the same basic plot that we created in episode 704. As you can see, the ending quantity is 2.718. This plot is our control plot. In order to see the impact of the random noise, we need to add the SDE solution on top of this control plot. But before we do that, let's create another button that we can use to generate a fresh plot whenever we click on the button. Okay, now we can use this button variable in our code and then suppress the plotting code for the ODE plot. Now let's add the plot for the SDE solution. This plot appears to be the same, but the SDE solution is actually sitting on top of the ODE solution. But it's difficult to see since I set the default value of beta to 0, which means there's no noise. In order to see some differences, we need to change the value of beta. Let's set up our control panel by pulling down the widgets. Before we pull down the plot, let's add some markdown so we can see the ending quantity. Okay, now let's pull down our plot and then hide some of this code. We are now ready to perform some analysis. Let's start by changing the value of beta from 0 to 10%. Click on the New Plot button to generate a fresh plot. There should be another time series plot on top of the control plot. If you zoom in, you should be able to see the quote-unquote noise in the solution. And because this is stochastic, your solution should be different than my solution. Also note that the ending quantity is no longer 2.718. You can generate another scenario by clicking on the New Solution button. You can generate multiple solutions by continuing to click on the New Solution button. As you can see, the ending quantities are all different. Sometimes the quantity is higher than 2.718, and sometimes the quantity is lower than 2.718. While this makes the ending quantity much more difficult to predict, this is a more realistic model of how quantities change over time. So, what's going on here? Well, the solution is still following the underlying ODE, but at every step it's adding some random noise, either positive or negative, to the solution. The magnitude of that noise is controlled by the parameter beta. The bigger beta gets, the more volatile the solution becomes. Let's try changing beta from 10% to 25% to see what happens. click on the New Plot button to generate a fresh plot. As you can see, there's greater volatility with a higher value of beta. Let's change beta to 100% to see what happens. This time, the individual time series plots look more like the time series plots for stock prices. You can see why this subject of stochastic differential equations might be of interest to those in the financial sector. Conceptually, by running multiple scenarios, you can generate a probability distribution around the underlying ODE that you can then use to develop a risk profile for a particular investment. A low value for beta might imply a low risk, low reward investment, and a high value of beta might imply a high risk, high reward investment. In addition to being used in finance, SDEs are also used to study molecular dynamics, neurodynamics, and the dynamics of astrophysical objects. Interesting, right? So to recap, a stochastic differential equation is just a differential equation plus some noise. When defining the SDE problem, you need to use the appropriately named SDE problem function, which takes both the ODE function and the noise function as arguments. In order to solve the SDE problem, you need to use an SDE solver, like the EM solver, which requires a time step keyword argument. You can replace the function f with any ODE function in order to create a stochastic version of that function. As an example, I converted the Verhelst equation from episode 705 into a stochastic version by following the same workflow that we went through in today's tutorial. All of my code is saved in my GitHub repository. There's a link to my GitHub repo in the description below. It's a lot more difficult to convert a system of differential equations into a stochastic version, but it is possible. The DifferentialEquations.jl package documentation contains an example of how to create a stochastic version of the solution to the Lorentz equations. So that does it for my coverage of stochastic differential equations. Believe it or not, there's only one episode left in this series. The DifferentialEquations.jl package has turned out to be a fascinating package that sits at the intersection of math, science, and computer science, where a lot of interesting things are happening. If you enjoyed using the DifferentialEquations.jl package as much as I have, then please consider going to their GitHub page to show your appreciation by leaving them a star. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, please consider making a purchase at the Doggo.jl online store. You can browse through a wide selection of Doggo.jl merch by clicking on the Store tab. For one-time donations, please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get early access to all of my new videos. Early access videos do not contain YouTube ads. New tutorials are posted on Sundays/Mondays. Thanks for watching, and good luck on your Julia journey.